Welcome to the Explainer. We're about to dive into a really fascinating question, something that touches on the very fabric of our universe. What if? What if the numbers that literally define our reality aren't random at all?
Okay, so let's get right into it. We have this amazing theory of particle physics, right? It's called the Standard Model, and it works incredibly well. But, and this is a big but, it all depends on about 20 different numbers. Think things like the masses of fundamental particles. The problem is, we have to go out, measure them in experiments, and then just plug them in by hand. We have absolutely no idea why they have the exact values they do. It's a huge mystery.
And here's where it gets really interesting. Every now and then we see these strange little hints of a pattern in the chaos. So take a look at this. It's the mass ratio of a specific particle state to a proton. The value we've measured is 1.608, which, that is just shockingly close to one of the most famous and fundamental numbers in all of math, the golden ratio, phi, which is 1.618. So, the question is that just a wild cosmic coincidence, or is it a clue pointing to something much, much deeper?
And that right there, that sets up the big mystery we're tackling today. Are all these fundamental numbers that define our universe just a random jumble of cosmic accidents? Or are they actually ingredients in some grand recipe? A recipe that follows a hidden, structured logic we just haven't figured out yet.
A good way to think about it is like this. The Standard Model is a perfect recipe for a cake. It tells you exactly how to mix everything together to get a delicious cake every single time. It works flawlessly. But what it doesn't tell you is why you need, say, exactly 2 cups of flour, or why the oven has to be precisely 350 degrees. The recipe works, for sure, but the numbers themselves, they're still a complete mystery.
So, how do we explain these mysterious patterns? Well, there's a new idea on the table. It's called the Geometric Scaling Framework, or GSF for short, and it's proposing a pretty radical new blueprint for reality itself.
Okay, so the core idea here is that our universe isn't just organized by space and time. No, the GSF says there's another dimension, scale. And here's the kicker. This dimension of scale isn't a smooth ramp. It's more like a ladder with distinct separate rungs. And on each one of these rungs, physics behaves in very specific, very stable ways. So what determines how far apart these rungs are? Well, it's not random numbers, that's for sure. It's a special set of mathematical constants called Poisson numbers. And you'll recognize the first one. It's the golden ratio, phi, that we just saw. But there are others too, like the plastic number, rho, and the Fibonacci constant, tau. These special numbers, they literally define the very structure of this cosmic ladder.
All right, so if the universe is built like a ladder of scales, what does that mean for the fundamental particles we see in our experiments every day? What are they in this new picture?
Well, in this new language, particles aren't just tiny dimensionless points anymore. Instead, the GSF introduces a new fundamental building block. It's called an H-cell. And it's basically the smallest, most stable geometric shape that can even exist on this scale ladder. And this picture really shows you how it works. A single stable H-cell, well, that might be what we see as a fundamental particle, like an electron, what we call a lepton. Now, if you link 2 of them together in a loop, you get a short-lived particle called a meson. And if you put 3 of them together in a triad, you get a super stable structure like a proton or a neutron, the baryons that make up, everything. All of a sudden, the entire particle zoo seems to be built from simple geometric arrangements of just one basic shape. It's kind of mind-blowing.
So what this framework does is it gives us a whole new dictionary for particles. It's a brand new taxonomy. The matter particles, the ones we call fermions, they're just different structures made of these H cells. And the force-carrying particles, the bosons, well, they're more like waves traveling in the corridors between the rungs of this cosmic ladder.
This geometric way of looking at things even gives us a really intuitive way to understand a super deep mystery in physics called quark confinement. The idea is that the Higgs cells inside, say, a proton are all connected by one of these corridors. Now, if you try to pull them apart, it's just like stretching a rubber band. The farther you stretch that corridor, the more energy it takes. And that's exactly why we never ever see a single quark all by itself in nature.
Okay, this is a beautiful, really elegant idea, for sure. But is it just a nice story, or is it actual science? Well, to find that out, there's only one thing to do. We need to see if it makes predictions that we can actually test against reality.
Let's talk about one of the biggest puzzles in modern physics, neutrino mixing. We know there are 3 types of neutrinos, and we also know they can morph into one another as they fly through space. This whole process is described by 3 mixing angles, and honestly, Their measured values have always just seemed totally random.
But the GSF comes along and says, nope, they're not random at all. In fact, it predicts they're just simple geometric slopes based on different powers of the golden ratio, phi. This angle card that comes right out of the framework gives you incredibly specific numerical predictions for all three angles. And get this, there's no fudging, no tuning any parameters. The numbers are what they are.
And the results? Well, they're pretty astonishing. Just look at this plot. It compares the GSF's predictions, those are the orange squares, directly against the values we've actually measured in experiments, the blue circles. I mean, you can see for yourself, the alignment is remarkably close for all three angles. What used to look like a bunch of random numbers now really seems to be part of a single, coherent geometric pattern.
And as the paper itself points out, the real power here isn't just in one single amazing prediction. No, the real strength is that this one single coherent idea, this scale ladder built from just a few mathematical constants, is making a whole bunch of different, precise, and testable claims all at the same time.
So here's the crucial takeaway. This isn't just a neat idea to think about. It's a real, legitimate scientific proposal. And why? Because it makes concrete predictions that can be tested and, this is the most important part, it can be proven wrong.
And that right there is the hallmark of any good scientific theory. The GSF gives us a clear checklist of ways to break it. For example, if future, more precise experiments show that those particle mass ratios start to drift away from the ladder's constants, the theory's wrong. If big experiments like Dune or Hyper-K pin down that final neutrino mixing angle and it falls outside the two specific values predicted by the GSF, then the theory's broken. Simple as that.
Everything we've talked about today, by the way, comes directly from a specific source. It's the fourth paper of the Geometrical Scale Framework Program, which is a Pisot scale ladder theory authored by Dr. Nader K. And that paper lays out this whole framework and all its bold predictions in incredible detail.
So this leaves us with a really provocative final thought to chew on. What if all those seemingly random numbers that define our entire universe aren't random at all? What if they're actually just the echoes of a deep, hidden geometric harmony? What if all of physics, the whole shebang, is just playing out on the rungs of a cosmic ladder we're only now beginning to see?